So let's start with Bellman-Ford algorithm, and Bellman-Ford algorithm is very much popular, you can say, in terms of supporting negative weights in the given graph. So we have already seen about De Castro algorithm, and De Castro algorithm may or may not work well with correct answer if the weights given in a graph is negative. And certainly if the cycle is negative, some of the weights of any cycle formed in a graph is negative, even Bellman-Ford also does not work, but it works well with negative weights. So always it gives you correct answer. How basically this algorithm works, roughly it uses the same thing, relaxation rule, as we have done in the case of the Castro algorithm, that if the distance of u plus cost of u to v is less than distance of v, then simply we will update distance of v as distance of u plus cost of u and v. It's the same as you can say in case of De Castro algorithm. So same method we will apply, but how many times relaxations rules we apply here, that depends on number of vertices. So if in our graph number of vertices, let's say 6, so how many iterations we will do? We will iterate the relaxation rules for how many times? 6 minus 1, that is number of vertices minus 1. So that is the number of times you need to iterate relaxation. So iteration for relaxation rules will run for how many times? Order of v minus 1. So if there are 6 vertices, I will iterate the relaxation rule how many times? 5 times. So let's take one example and try to understand how basically Bellman-Ford works, even true for negative weights. So let's say there are vertices like A, B, E, this vertex is let's say C, this vertex is let's say D, and cost matrix for each of the vertex to another vertex is also given. So assume that this is a directed graph and source distance is always 0, and this cost of u to v is 6, and this is 4, and this is let's say 5, and b to c path is given as minus 2, and there is a path from d to c which is also minus 2. This d to f path is minus 1, and then c to e path is 3, and b to f path is given as minus 1, and e to f path is given as 3. So you can see the diagram from here. So this is the let's say graph is given to you, and you try to find out single source shortest path distance from A to all others by using Bellman-Ford algorithm. So first of all, how many times relaxation rule will work? It will work for 1, 2, 3, 4, 5, 6. So we will run the algorithm for how many times? 5 times. Means what? 5 times iteration will be done, and iteration will be done for relaxation on what? It will done over all the edges given in a graph. So first of all, you mention about edges in our graph. So let's say edges are written like AB one edge, AC is another edge, AD is another edge, and another edge is let's say BE is one more edge, and then we have CE is another edge, then we have DC as another edge, we have DF as another edge, we have EF as another edge, and at last we have let's say CB. How many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, is correct. So first of all, we will mention about the edges. There is no sequence ascending or descending order. You can mention in any way. So first step we have done, we have mentioned all the edges given in our graph. And initially, just like our Bellman-Ford, we will assume, let's say we are starting with source vertex A, and we will assume the distance to A is 0 and distance to all other vertex is infinity. So A to B is infinity, A to C is infinity, A to D is infinity, reaching E is infinity, and reaching F is also infinity. So we have updated like this. So this is the first step, and now we will start applying relaxation rule. So in the first iteration, you can see we are iterating over all the edges. So in all the edges, it is starting with 0. So the right now cost of reaching b is infinity. So 0 plus 6, which is less than infinity, so we'll update it 6 here. 0 plus 4, which is infinity is less, so we'll update it with 4. And 0 plus 5, so infinity will be replaced with 5. And then let's say AB, AC and AD we have done. Let's try for BE. BE cost is infinity, so 6 minus 1, we are getting a better cost, we'll update it 5. So BE we have done. CE, so CE cost is given as, this is right now 4 plus 3, 7, but right now we are maintaining 5, so we will not update it. DC cost we can check. DC cost will be 5 minus 2. So right now we are getting 4. So we can update it as 3. After this we got 3 cost here. And then DF, we can maintain DF as 5 minus 1. So we can maintain it as 4. So after this we are getting 4. And for EF, right now it's a 5 plus 3, 8 we are getting, but right now it's a 4. So we will not update. And CB we can check. 3 minus 2. So right now its cost to reach B is 6, so we can update it with a better cost, that is 1. So this is all we got after first iteration. So this is about the first iteration. This is the things we have got. Again we will apply this rules in second iteration, and let's see whether we are getting a better results or not. So right now we are having result here 1, 0 plus 6 is greater, so we will not update it. Right now here we have result as 3, 0 plus 4, we are getting bigger part, so we will not update with the last one. Right now we are having cost 5, we are still getting 5, so we will not update it here. So in the next part we can check it. So in the second iteration we will go through edges by edges. We will check for A to B. Right, new cost is 6, so we will not update it. And then A to C also, no updations, we are getting better cost. A to D we are not getting any better cost, still 5 we are getting. B to E, right now E is 5, so 1 minus 1 you are getting a 0. The better cost you are getting, you will update for BE in second iteration. And then after BE you can check for CE also, you are not getting better cost. 3 plus 3, 6, it is 0. For EF you can see 0 plus 3, right now cost is 4. So EF again you can maintain it with 3. So 0 plus 3 is better you are getting, so you maintain it like 3. And no other changes you can find in any other edges given in the graph. So you can see in the second iterations you updated two edges, B to E with better cost 0 and E to F with better cost 3. We will go for third iteration as there are 6 vertices, so we will move up to 5 iteration. Third iterations, if you go through the same AB, AB, AC, AD, all these sets of vertex, you will get no changes in any cost. So it remains same. So manually if you see, if there is no changes, you can stop the process, but computer will stop only after n-1 iteration. So final weights you can check it, what you have got. Basically you got A2 itself is 0 cost, reaching B taking cost 1, reaching C taking cost 3, reaching D taking cost 5, and reaching E taking cost 0, and finally reaching F we got a cost of 3. So from here you can understand Bellman-Ford works very good even with the negative values. Yes.